Hey everybody, this is Math 219, Introduction to Differential Equations for the fall 2020 semester. My name is Özgür Kişisel. So I'll be lecturing here and I'll be writing at the same time that I'm talking. This will be the initial lecture for the course, and the lectures will go on in a similar way. For your questions related to this lecture, you could ask them during the online office hours, or simply write to me, or simply write a comment below the video. I'll try to answer them all. Okay, so we start by asking, what is a differential equation? And simply, a differential equation, most naive terms, is any equation that contains derivatives. So, an equation containing derivatives. Of course, along with algebraic operations. Okay, so typically you have some variables in the equation, and these are either dependent variables or independent variables. Maybe I could explain this best through a simple example. So suppose we have a function x depending on t. Okay, here is a differential equation. X prime denotes derivative, is equal to t squared times x plus e to the power 2t. Okay, just to repeat, x prime is the time derivative or t derivative of x. T could be time or something else, it doesn't matter here. And on the right hand side, we have some function of t and x. Here it is t squared times x plus e to the power 2t. Never mind about how to solve this for now, it's just an example of a differential equation. So here, t is the independent variable, and x is the dependent variable. Okay, so what can you ask about differential equations? Typical questions are, given a differential equation, one often would like to find all solutions. That's one possible question. An alternative question could be find a solution satisfying some additional conditions. There are some further questions one might be interested in. For instance, you might not want to find actual the solutions, but say something about their qualitative behavior. Okay, I'll talk more about these in the future, of course. Now, the example we gave was just a single equation about a single dependent variable. You could have some other alternatives. So let's say this time we have two functions of t, xt, and yt. Okay, so we have two dependent variables, x and y, and one independent variable t. Okay, I'll write the so-called system of differential equations. Here it is, x prime is equal to, let's say, x times y. Well, I'm making these equations up. They don't mean anything special. They're just examples here. And y prime. Now, a bit of notation here. I'm writing t here. I didn't write t here, but it doesn't matter. I could have omitted the t's here, but we should understand that both sides are functions of t all the time. Okay, a second equation. And let's say this is x plus 2y plus t. Okay. So I have one equation for each dependent variable, but the right-hand sides are kind of mixed up. I mean, it contains both dependent variables and possibly also the independent variable. Okay. This is a system. The previous example was a single equation. And, okay. So here you would want to find x and y at the same time. I'm just finding one of them doesn't make too much sense. You have to find a pair that satisfies both equations. Okay. Now, another type of example, quite different. This time, we have a function, use a function of not just a single variable, but two variables, let's say x and y. So it's a multivariable function, which looks like this, u of x, y, the type of thing that you studied in multivariable calculus. Okay, now I want to write some differential equation for this, but this time, if I do u prime, it doesn't mean much. I mean, there are two variables, so I have to really tell you which derivative I mean. They should be partial derivative. So, but something like this might be sensible. For example, del u del x plus del u del y is equal to, let's say, x minus u. This is a u. Okay. Again, this is just kind of some arbitrary equation, but the important thing for this example is you need to have partial derivatives because you have a multivariable function. Okay. Now there's a distinction between the case where you have partial derivatives or where you have simple derivatives. So that brings up this important definition. So if you have just one independent variable, like the t in the first examples, then we say the differential equation is an ordinary differential equation. And since this is too long to write each time, it is abbreviated as ODE. By the way, differential equation is also abbreviated as DE, just to say. If you have more than one independent variable, let me write this short form. Okay, in this case, you say you have a partial differential equation, since you have partial derivatives now. And the abbreviation you might guess is EDE. Okay, these are just some names for now, but well, we should know the terminology. And well, this course 219 is mostly about ODEs, but at the end, in the last 2 weeks, we'll also look at some PDEs, some simple ones at least. But if you want to understand PDEs, you definitely have to first understand ODEs to some level. Okay, now another issue. In the example so far, we just had first derivatives, either ordinary or partial, but you could have higher derivatives. So suppose we have x of t now. Let's look at something with the second derivative. So I have x prime prime plus, let's say, 2 times x prime plus 3 times x. And on the right, let me put a t. Okay, this is a nice differential equation. It contains second derivatives, this prime prime, as well as the first derivative. Okay. Now, the more derivatives you have, okay, the more entangled things become. So we need a definition for that. Well, how many derivatives do we have at most on some function? So the highest derivative appearing is called the order of that differential equation. Let me write D for short. Okay, if you would like to see some concrete examples, 2 of them. So let's say x prime 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 plus 2x double prime plus x equals t, something like that. Here, this is order 3 because you have 3 derivatives on top of x and no more. But some possible confusion if you have okay, let's write some other equation like this. This time I have x prime prime cube and then x to the 4th derivative. Okay, this is order 4. Taking powers, I don't care at all. I mean, it's the number of derivatives that you have that's important. The highest derivative appearing is the 4th derivative. Here you have the cube of the second derivative, but still that's about the second derivative. What we're interested in about order is the highest number of derivatives around. Okay. Now some general comments. So differential equations appear a lot in real-life problems. These could be about engineering problems, problems in science, problems in economics or social sciences. Well, I mean, the variety is really mind-dazzling, and some differential equations, which first were studied in some areas of science or engineering, later turned out to be important in other branches as well. Now, why do they appear? That's kind of a philosophical question. I don't know, but maybe one answer is rates of change. The rate of change is some derivative. The rate of change are sometimes easier to formulate in real-life problems. So sometimes easier to formulate, let me say, and like that. I mean, sometimes you don't know the actual algebraic equation for your variable, but you know something about this rate of change. And then from there, you want to find the actual values of the variable. That's why differential equations appear so often. Okay, those those were my first comments. Okay, now one warning is solving differential equations explicitly, I mean finding the function. Of course, that's your goal if you can do it, but that's sometimes difficult. I mean, and this difficulty not just meaning that, you know, you may not know it or something, but I mean, it might be out of reach. It might be something that nobody can do. And what do you do then? Well, there are two things to say here. First of all, there are some simple equations that you can solve, and you want to know how to solve them. And you might say, okay, what if the equation is not simple? Yes, of course, that can happen, but simple DEs occur in applications more often. That's kind of a key thing to know. Okay, you might know this, how to solve this simple thing, but since it is simple, it tends to occur more often. There's some kind of interesting thing like that. And so you may not worry too much about not knowing the complicated ones. But occasionally, sometimes you come up with a complicated DE and you cannot solve it. If you cannot solve it, if one cannot solve explicitly, there is still some value to study this differential equation. You could look at the qualitative behavior of solutions. I mean, somehow you can say what the solutions look like without really solving them. And another way to go is to look at numerical approximations. So you may not know the function, but using a computer or otherwise can approximate it. And that's done a lot. Okay, so these were some general comments. Now, let's talk about solutions of some first order ODEs. So kind of the first thing to look at, right? The order is as simple as possible, and it's an ODE. You don't have partial derivatives. That's where we should start. Okay. In general, it will look like this. So let's say our variable is y, dependent variable, and the independent variable is t. So the equation will look like this: y prime equals something, and that something will be a function of t and y. Or another notation, instead of y prime, sometimes people write dy by dt. It just means the same thing. Now, what is a solution here? Solution. First of all, solution is a function. A function y of t should be, well, what's its domain? On some open interval AB. I mean, one should tell what interval one is working on. By the way, A could be minus infinity, B could be plus infinity, those are possible. Okay, of course, satisfying the differential equation, right? Something like that is called a solution. You might have many solutions to the same differential equation, and you typically do. So let's start from maybe the most basic things we can write down. Let me write something like dy dt equals sine t. Okay. Yeah. How would you solve this? Well, this is really simple. The right-hand side is sine t, so there's no y there, right? It's just t. So you just have to integrate. I mean, this is not really differential equations. This is calculus. So just integrate sine t. And if you know how to integrate that, you're done. So you have minus cosine. But please be careful. I need to put a plus c to get all possibilities. Right? You don't want to miss any solutions. So c is any constant. So this was calculus. And if you want to graph the solutions, okay, minus cosine t, what does it look like? Cosine 0 is 1, so minus of that would be minus 1. We'll go up and down like that. Can also continue to that side. That's minus cosine t. Now, of course, I can add to it any constant that I like. So that would shift the graph up or down, right? So another possible solution. My drawing is not maybe very good, but they should be equally spaced. It should just be a shift of this. Okay, you have this infinite family of solutions, and if you really draw them all, those would fill the whole plane, right? Any two solutions are just vertical shifts of one another by a constant. Yeah, my drawing is really bad. This distance should be the same as that distance, but it's not. Okay, now let's do a second example. This time, on the right-hand side, I'll put y. Now, this is not calculus. It's differential equations because I cannot simply integrate. What happens if I try to integrate? Y is equal to integral y dt. Fine, but what else? I mean, I don't know y as a function of t, so there's something in the integral which I don't know. Therefore, I don't know how to integrate it, so I'm stuck here. This method doesn't work. You cannot do y times t, right? That doesn't work. That's not the antiderivative of that. Y is not a constant. So this method doesn't work, and in this course, well, we should find a way to get around this. Okay, let me not tell you how to really do this and how to find all solutions right now. We'll do that very soon in the next lecture. But just observe that okay, let's try to read this. Find a function whose derivative is equal to itself. And by experience, we know such a function. Y equals e to the power t is a solution. Just because we remember it from calculus. I mean, if you take the derivative of e to the t, you get e to the t back. This is not a systematic way yet, but this is some simple observation. Okay, we found one solution. Can we find others? Well, some more careful looking at this also tells you that if you multiply this by any constant you like, it still works. Or any c. Okay, again, we have some free constants, but this time it's not a plus c as in calculus, right? It's a times c. So the constant appears in a different place. We can still not be sure at this point whether we found all solutions. Actually, it is true. These are all solutions, but we'll see that later. If we graph them, what do they look like? T times e to the t. So first e to the t, at 0 it is 1. goes up like this somehow. If you multiply this by c, you'll be scaling it multiplicatively. So these are some graphs for different values of c. If you pick c equals 0, you just get the x-axis. And for negative values of c, that could go down. Again, if you were able to draw all of these for all values of c, those would fill up the plane. And if you take any two of them, their ratio is constant. Their difference is not. Okay. Now, if we had an additional condition in this example, such as, let me make up one, y0 equals 5, okay, then we would have a unique solution. Well, I didn't yet prove that these yt equals ce to the t are all solutions, but assume that for a moment, okay? In that case, y0, which is 5, must be also equal to c times e to the power 0, which is c. So this immediately tells you that c must be 5. So y is 5 times e to the t. This time you have some concrete honest function, and this is a single thing which satisfies both the differential equation and this condition. So conditions such as this one, the value of the function at one point, that's called an initial condition. So I'll make a more careful definition later. But initial condition. Okay, so far so good. Now, in the second part of this lecture, I want to introduce some nice graphical way to analyze differential equations. This is not a method for solving them, but this is a method for understanding what the solutions kind of looks like. Okay, the title is Direction Fields. Okay, now here's the story. Suppose you have a first order equation like this one. Okay, we want to find the solutions. So the solutions have graphs, and we want to find these curves on the ty plane. So we want to find the solution curves, so-called, on ty plane. I mean, we want to find them geometrically somehow. Okay, so what do we know about the relation between a derivative and geometry? Now, dy dt, this is a derivative. Well, if we fix a point like t0, y0, derivative is a function, but if you pinpoint a point, I mean, if you fix a point, then this is equal to something geometric. This is equal to slope of tangent line to the graph of function yt at the relevant point, right? I mean, I need to write a little bit of words here, but it's a slope. It's the slope of a tangent to what? To the function that you're looking at, right? So graph of the function that you're, that's the geometric meaning of derivative. Now, let's think about our problem once more. dy dt equals f of ty. So you are given f and you want to find y. So if you are given f, then you know all these slopes, and you know these slopes at all points. So if we know f, then this means we know these slopes at all points. And what we don't know and what we want to find are the curves, right? We want to find the curves. If you knew these curves, if you had these curves to start with, you could easily draw the tangents by hand. This is kind of the reverse problem. You have the tangents and you want to reconstruct the curves. Okay. Now, we could more or less visually do this to some extent. We could draw line segments with these slopes all over the plane, and then we could try to figure out which curves fit these slope lines so that these are really the tangent lines. So we construct a direction field, so-called, or another name is slope field. So how you do this is, at many points on a plane, ideally at all points on the plane, but this is not possible, of course, practically. So choose as many points as you can on the plane and put line segments of slopes f of ty. Of course, ty is the coordinates of your point. So when you change the point, this value of the function will change, therefore the slope will change. So you'll have varying slopes all over the plane. And once you're done, then try to draw the curves tangent to these line segments. You might say there are many curves tangent to a given line segment. Sure, but this is going to hold at all points. So this is a real big restriction on the curve, right? You start somewhere, you begin as a tangent, and later you still have to follow the other tangents. And you'll see soon that there's essentially one way to do this. Okay. Now let's work on an example to make this all clear. Okay, let's suppose we have y prime equals y times y minus 1. And let me draw some dy plane out here. Okay. Now let me change the color of the pen for a moment. Okay, at each point, or at as many points as I can, I want to put lines with the correct slope. So for example, at 0, 0, this is your f, right? F of dy. So at 0, 0, the value of this function is 0 times minus 1, so it is 0. A line segment of slope 0 is horizontal line segment. So that's what I put here. Well, the same goes for any value, I mean, any point with y value 0. So along this axis, I'll have horizontal line segment. Let's put some other value like 1 over 2. Now 1 over 2 times minus 1 over 2. If I take y equals 1 over 2, I'll get minus 1 over 4, right? So let's say this is 1 over 2 here. At 1 over 2, I should put a line segment of slope minus 1 over 4. First of all, what is negative slope? Negative slope is oriented. Okay, I don't know how you see my hand, but it should be like y equals minus x or along this direction. So minus 1 over 4 would be something like that. And for any point with y value 1 over 2, that's going to be the story. If I go up to y equals 1 somewhere here, again, 1 times 0, that's 0, so these will be horizontal back again. And in between, I can sort of sense what's going to happen. Between 0 and 1 over 2, okay, the value of this product will be negative, but somewhere between minus 1 over 4 and 0. So this will again be negative, but maybe more horizontal than the one above. And same here. So what happens in the region below? What happens for y less than 0? If y is less than 0, negative number times negative number, that's positive. So I get positive slopes, which are tilted this way. And you can figure out that if you go further down, the slopes will increase. Kind of the same thing happens up here. If y is greater than 1, then some number greater than 1, well, this is positive, so slopes are positive here and increasing if you go. Okay, I'm getting out of the graph, but I think we get a picture. This is kind of what all slopes would look like if we were able to plot them all. Now, let's switch back to black. Now, the solution curves would be some curves so that they're tangent to all of these lines at all of their points. And it's like following the flow of a river, right? So, I mean, if I'm here at some point, those would take me down and eventually asymptotic to this line maybe. And if I flow backwards, that would go somewhere here. And same if I'm here, same here, and so forth. So we see that the solution curves between these two values of y should approximately look like this, starting somewhere around y equals 1 and eventually asymptotically decaying to y equals 0. Whereas if we start down somewhere here, these will take us up here, right? And we can expect some curves that are becoming asymptotic to y equals 0. If I start up there, I cannot draw it really very well, but this will go up and to infinity. So the curves for y greater than 1 tend to go up to infinity. Now, we didn't solve any differential equation here. This is just some graphing, but it still tells us something, right? I don't know how to solve this equation at this moment. We'll see that in the next lecture, I suppose. But still, we have some idea what the solution curves look like, right? So if you start somewhere between 0 and 1, they go down to 0. If you start somewhere below 0, you go up to 0. If you start somewhere above 1, you go up to infinity. So that's some qualitative information that we were able to get without really solving anything. The nice thing is you can do this procedure for any first order equation that you like. I mean, it doesn't matter what you have here on the right hand side. So this is quite general. There are no tricks. You just compute some values, draw some slopes. And by the way, this is very suitable to be done on a computer if you don't want to do it by hand. Okay, finding actual functions, explicit functions, is another story. That would be solving the differential equation, and we'll have the whole semester to talk about that. Okay, so that's all for this lecture. Thank you very much.